So I'm back, and today we are going to do areas in polar coordinates. This will be section 10.4. This section is not so difficult, except that whenever you do areas or any calculations in polar coordinates, it's best to graph the polar curve in order to see what you're doing. So let's start off with a warm-up. I want to discuss a polar curve for you that we did not discuss before. So it's r equals theta. This is an interesting polar curve because when you graph r equals theta, remember a point is of the form r theta. R is essentially the distance to the origin, and theta is the polar angle. When theta is 0, r is 0, and as theta gets bigger, for example, theta is pi over 4, r is pi over 4. So as you go around and around and around, you spiral around the origin. So this is a spiral or so-called helix. Okay, this is just an example that I wanted to cover. This is not going to apply to the area question. So let me get started with the area question. So 10.4 areas in polar coordinates. Okay. And how is that going to go? So you have first of all, we're going to need to know something that you probably have encountered before. So we need to know this. Suppose I have a circle. I don't need actually to actually draw axes. Suppose I have a circle and I have a sector in the circle. And the sector encompasses a central angle of theta, and the circle has radius r. So then the area of the sector is given by 1/2 r squared theta. So that's actually a well-known formula. And in fact, when theta is 2 pi, you get the whole circle. You get 1/2 pi r squared as the formula, which is a well-known formula for the area of the circle. Okay, so we're going to use that. Okay, so what we're going to do is we're going to consider now a polar curve. R equals f of theta, where theta is between two fixed angles, alpha and beta. And what we're going to do is we're going to look at how our polar curve looks. So here's our polar curve. And we're going to look at the area encompassed by the polar curve. So let's consider the little sector-like region. It's not really a sector because this is not part of a circle, but this sector will be determined by two angles, an angle called theta I minus 1, and then a bigger angle, theta I, and then the angle in between is called delta theta. So delta theta is theta I minus 1. Okay, so now this region, which I'm going to shade in right now, that we want to compute the area of the region is approximately a sector. It's not exactly a sector, but it's approximately a sector. So its area, the area of this particular region is something close to being 1/2 r squared times the angle it encompasses. So it's 1/2, r is f of theta, so it's 1/2 f of theta I minus 1 squared times delta theta. So and that's the ith area. If we cut up this curve into a lot of these little sectors, we'll get, so this would be the ith sector, so then the total area would be given by a sum over I of 1/2 f of theta I minus 1 squared delta theta. And now we'll take the limit as delta theta goes to 0, and then we get the area under the polar curve will be an integral now, this taking place from alpha to beta, of 1/2 f of theta squared d theta. So this is the formula I wanted to showcase. Okay, so we're going to use this formula to calculate some examples. Okay, so the first example I'm going to do is directly from the text. It's the example given by one loop of the 4-leaf rows. So, and the 4-leaf rows is the equation r equals cosine of 2 theta. And so let me draw a picture of the polar curve. So it looks like this. This is our 4-leaf rows. We want one loop of it, so we're interested in this area. So this area is we might as well do twice half a leaf, half a loop. So we're going to compute the area of half a loop. Compute half the area of a loop and multiply that by 2. That'll save us some work, you'll see. Okay, so now what is that? Well, if you look at the loop, let me phase in it. Half a loop is this greenly indicated curve, and that corresponds to theta between 0 and pi over 4. That's easily checked. So 0 is less than or equal to theta is less than or equal to pi over 4. And so now we write down the area. The area of half a loop is the integral from 0 to pi over 4 of 1/2 r squared, or 1/2 cosine of 2 theta quantity squared d theta. But now we want to multiply that by 2 because we only got half the loop. Okay, so this is going to be, that's going to be the area as an integral. We want to compute that. So what I'm going to do is I'm going to let u equal 2 theta. I'm going to do a u substitution. Du is 2 d theta. And so 1/2 du is d theta. And this integral becomes what? It becomes twice the integral of the, oh yeah, so what is theta, what is u going from? Well, if theta is going from 0 to pi over 2, u is going from 0 to pi over 4, I should have said. U is going from 0 to pi over 2. So it's twice the integral from 0 to pi over 2 of what? Of 1/2 cosine of u, quantity squared, times d theta, which is 1/2 d theta. And if you get all the fractions together and bring them outside, this is 1/2 the integral from 0 to pi over 2 of cosine squared u du. We've done this integral many times in this class. It's theta over u over 2, not theta, plus sine 2 theta, 2u over 4, evaluated from 0 to pi over 2. And if you stick it in, you'll get pi over 8 as the answer. So pi over 8 is the final answer to this problem. Okay. So let me provide another example. Here's another example. Inside the curve r equals 4 sine theta, and outside the curve r equals 2. Let me first of all figure out what the graph of r equals 4 sine theta is. So r equals 4 sine theta, the way we figure that out is we multiply both sides by r. So r squared is 4r squared sine theta. So r squared is x squared plus y squared. I'm converting to rectangular, and it's not 4r squared, it's 4r. So that's 4y. So x squared plus y squared minus 4y equals 0. So x squared plus y squared minus 4y, I'm completing the square, plus 4 equals 4. So x squared plus y squared, oops, not y squared, but y minus 2 quantity squared equals 4. So this is a circle of radius 2 centered at the point 0, 2. So 0, 2 in rectangular would be here, 2 units up, and it's this circle. It's a circle. And the circle r equals 2 is also a circle, but that's centered at the origin, so it's this circle here. So we want to be inside the first circle and outside the second circle, so we're looking at this region right here. But by symmetry, it's enough to look at 1/2 of that yellow stuff, so that would be this green area, and we multiply the area of the green part by 2. Okay, so we have to figure out the intersection point here, because that's going to be a key point. So this point right here is one of our intersection point. So we need to set, let me do the calculation on this side. We need to set 4 sine theta equal to 2 to get the intersection point, because r equals 2 and r equals 4 sine theta of the curve. So sine theta is 2/4 or a half. So that means that theta is pi over, that looks like to me saying that theta is pi over pi over 6, right? So theta is pi over 6. Sine of 30 degrees is 1/2. Okay, so that's theta equals pi over 6. And then the other limit, so theta is starting at pi over 6, and then it goes up to theta equals, it looks like pi over 2. So that's, now we've just looked, that's the green region. Maybe I should do it like this, the green zone. Okay, so now we have the green zone. Okay, so now what are we trying to do? We're trying to calculate the area of the green zone. The area of the green zone, is equal to the area area determined by r equals 2, that's the outer curve, minus the area determined by r equals 4 sine theta. So we have to calculate the difference of two areas. So this is going to be given by the following thing. Let me go to my notes. So so actually it's the other way around. I messed that up. So so let's call the two circles well, no, let's just do, let me just write it out. So it's the area given by r equals 4 sine theta minus the area given by r equals 2. So let's compute that. Well, it's going to be just the area of the difference of the areas of two polar curves. And so, so this is going to be the integral from pi over 6 to pi over 2 of 1/2 f of theta squared. So f of theta in the first case is 4 sine theta, so 4 sine theta squared d theta minus the integral from pi over 6 to pi over 2 of 1/2 2 squared d theta. Okay, so these integrals are not hard. Let me do the calculation quickly. So the first integral is going to be the integral of 8 sine squared theta. So that's going to give me a theta over 2 minus sine 2 theta over 4 from pi over 6 to pi over 2. And the second one is going to be, which we're subtracting, is going to be given by twice the difference between pi over 2 and pi over 6. Okay. So I will spare you the drudgery. I did this calculation, and at the end of the day, the whole thing I got was 2 pi over 3 plus radical 3. But that's not the final answer because we have to multiply the final answer by 2 because we're only doing the green zone. So the final answer, which I'll put here, is given by twice that expression. So that would be 4 pi over 3 plus twice radical 3 if I haven't made a mistake. Okay, so that's this example. Okay, so the last topic in this section is arc length in polar coordinates. And the idea is to consider the points on a polar curve are given by r equals cosine, x equals r cosine theta, and y equals r sine theta, where r is f of theta. So so now that tells us that this is and theta is going from alpha to beta, let's say. So this is giving us a parametric way of expressing the polar curve. And so the arc length, L, is the integral from alpha to beta of the square root of x prime of theta squared plus y prime of theta squared d theta. Now we have to compute what that is. See, x is f of theta cosine theta and y is f of theta sine theta. So I'll spare you all the calculation. It's boring. You'll get, it's the integral from alpha to beta of the square root of r squared, which is f of theta squared, plus r prime of theta quantity squared d theta. So that is the arc length formula of a polar curve. Okay, so I'm going to do an example, and that'll be it for today. It's a short lecture then. Okay, so here's an example. The length of r equals 1 plus cosine of theta. Now this can be graphed. We've graphed it already, in fact. And what you get, it's a cardioid that looks like this. While r equals 1 plus cosine of theta is this curve here. And what I'm going to do is I'm going to take, since there's symmetry, obvious symmetry, I'm going to compute the area of the green zone. And the green zone occurs when theta is between 0 and pi. So, so according to our formula for arc length is the integral from 0 alpha to beta of the square root of f of theta squared plus r prime of theta squared d theta. And so what is that in this case? Is the integral from 0 to pi of the square root of f of theta squared, so that's 1 plus cosine of theta quantity squared, plus r prime of theta. R prime of theta, by the way, is negative sine of theta. So if we square it, we get sine squared theta, and then there's a d theta. And the rest of this is to calculate this integral. And by the way, since we're doing not just the green region, but twice it, we should multiply it by 2. So we get twice the integral from 0 to pi of the square root. Okay, so if you expand it out, you're going to get 1 plus 2 cosine of theta plus cosine squared of theta plus sine squared of theta d theta. And this becomes twice the integral from 0 to pi of the square root of what? The square root of 2 plus 2 cosine of theta d theta. Okay, so how do we do this integral? So the book suggests a trick for a similar integral. I'm doing a slightly different variant of the book's exercise. It says to take the square root of 2 plus 2 cosine of theta and make it multiply by the conjugate. So that would be 2 minus twice cosine of theta over the square root of 2 minus twice cosine of theta. That's multiplying by 1 in a very strange way. And the numerator becomes the square root of 4 minus 4 cosine squared of theta. And the denominator becomes the square root of 2 minus 2 cosine of theta. And then we can factor out a 2 from the numerator, bring the 4 through the square root, that's a 2. And then what's left over in the square root is 1 minus cosine squared theta, which is sine squared theta. We're taking the square root of that, so we get twice sine theta over the square root of 2 minus 2 cosine of theta. So we have to, so that's what the integrand becomes. And I'm going to have to integrate that. So let me put a new. Let me recover what I've just gotten rid of. So the area, the length, I mean, is the integral from 0 to pi multiplied by 2 of the square root of 4. I'm sorry, the square root of sine. No square root anymore. We got rid of that. It's the sine of theta d theta over the square root of 2 minus 2 cosine of theta. And if you stare at this, you see there's a nice u substitution. U equals 2 minus 2 cosine of theta you can do. Then du is plus 2 sine of theta d theta, or in other words, so what does this become? This becomes, so we have a 2 sine theta d theta because we can bring the 2 into the integrand. So this is the integral. What is the integral? So when theta is 0, u is 0. And when theta is pi, u is 2 plus 2 is 4. And then we have du over the square root of u, or in other words, the integral from 0 to the 4 of u to the minus 1/2 du, which is easy to do now because that becomes u to the 1/2 power. We have to multiply by a suitable fudge factor. It's going to be minus 2 u to the 1/2 is going to be the antiderivative, u going from 0 to 4. So it's going to be minus 2 times, did I get this right? Did I mess up the antiderivative? Let's see. So no, this is wrong. It's a plus 2. So plus 2, twice u to the 1/2, its derivative is u to the minus 1/2. And then we plug in the limits of integration, we get 4 to the 1/2 power, which is 2 minus 0. So the answer is 4, should be 4. Okay, so that is it for today. We've now covered this section of the text, which was section 10.4. We're done with 10.4.